Hello, everyone. In this lesson, we're going to talk about how to determine domains of functions that contain trigonometric functions. Before that, I'd like to review the domains of these functions, right? Sine, cosine, tangent, cotangent, and secant, cosecant. There are two perspectives I'd like to go over. The number one is the ARD. Okay. And we know that ARD is the essential for trigonometry, which A is about angle measurement, and R is about reference angle, and D, of course, is the definition of these functions. So when we are we're determining the domain of these functions, the first thing we do is that first let's look at sine and cosine. From the definition, we can tell R is the denominator for both sine and cosine, okay? And the way that we have chosen R, meaning that R is always positive because X and Y cannot be zero at the same time. Because R can never be zero, therefore, any angle will have a blue, any angle we will have red, or, some of you would like to use the Y over R, okay, and X over R. So in this regard, you can see domain of sine, cosine are all real numbers. Okay, so let's write down domain of sine, domain of sine and the cosine are the same, which is all real numbers. Okay, it can be any angle, however you measure it. It could be zero, could be positive angle, negative angle. Any value is okay. All right. With that understanding, let's look at the domain for cosecant. Okay. So here, cosecant. So let's look. We're going to look at the functions in these relationships, right? For domain of sine and cosine, we group sine and cosine together, right? Their domain and range. Their domain and range are the same, actually. Okay, so the range. Let me put a range here. The range of sine and cosine is that I'm going to put just a little table here. And there we go. So sine is between -1 less than equals to sine of A less than equals to +1, and cosine has the same range. Okay, so this is very important and very, very useful as you move forward. Okay, domain range. The second group we're just going to look at the denominator, right? So denominator cosecant. Okay, so let me make a table here. Okay, cosecant. Cosecant's denominator is the blue or the Y. Okay, so R over Y. And what else has the denominator blue? That's a cotangent. So these two functions will have the same domain, which is X over Y for cotangent. So to determine the domain for cotangent and the cosecant, and we understand that Y cannot be zero. Y cannot be zero. So if Y equals to 0, those terminals cannot be the input angles terminal. Okay, so Y cannot be 0. So then we'll be asking the question, when does Y equal to 0? when we measure angles, one will be the blue equals to 0, right? When will the blue be 0? So you'll be thinking about that. Yes, we're gonna draw any angle, right? So when will the blue be 0, right? In this case, blue is 0. Do you see that? You see one is horizontal, blue is 0 because we only have X. And the other terminal where blue is 0 is the negative direction of x-axis. So these are the two terminals must be excluded from the input for cosecant and cotangent. That's how we determine. So once we determine the terminal that it cannot be, right, then we will be able to tell the domain. The domain of these two functions, okay, the domain of these two functions would be what are the angles that terminate here, either terminate in the positive direction or negative direction of the x-axis, and those angles will be the angles cannot be k pi, the multiples of pi. Why? Because if k equals 0, the terminal is here. If the k is 1 and it's pi, so then we can, the domain cannot be any multiples of pi. And there we go, we got the domain. And what about the range? The range of these two functions, we're not going to consider at the moment, okay, because we have talked about it before, and it's going to take a much longer time to explain from the beginning. So just now, we just work on the domain. So that's for cosecant and cotangent, okay? And the next one will be tangent and secant, okay? So for these two functions, we're going to make another group, okay? One is a secant, and the other one is tangent. They have the same denominator red. They have the same denominator red, or x, okay, or x. So it's y over x, and this other one would be r over x. So the domain obviously will be determined by making sure we're not going to get not a 0 denominator. So when will the denominator equal to 0? That's when x equals 0. When will x be 0? Right? When will x be 0? So if we draw any terminal, right? In this case, x is not 0, right? And when will x be 0? The red equals 0, right here. We only have blue, we only have y, no x. And the other terminal will be this one. So any terminal that ends, any angle that terminates on the y-axis, those are the angles that cannot be the input for tangent. So we know how to express that, okay? So those angles would be, okay, the angles that cannot be the input for tangent and secant, those angles would be A cannot be pi over 2. It cannot be positive, negative pi over 2. It cannot be positive, negative pi over 3 pi over 2, and so on and so forth. Okay, so 5 times of it. So odd number multiples of pi over 2. So these are the angles that it cannot be the input for tangent and secant. So to express all of these, we just write the odd number. Odd number would be 2k plus 1 or 2k minus 1, multiply pi over 2. It cannot be odd number multiples of pi over 2. We're not going to talk about range in this section. We just focus on the domain. Another way to determine the domain of these functions, if you're good at the unit circle, if you are good at the unit circle, okay, combining with the unit circle, okay, so I'm going to put a unit circle right next to it, okay, I'll put it right here, make it a little bit small, okay, you draw the same conclusion because if you look at the entire unit circle, okay, let me just make it a bit larger so you can see better. All the blue numbers, right? You can see no matter where you position the terminal, you always have a blue number. Okay, that means for any angle, you're going to have a ratio, you're going to have a sine ratio. And for cosine, same thing. No matter where you position the terminal, the red will always be, because the denominator is always positive. So that's, you have blue number, you have red number, so the domain is all real numbers, and the range is from -1 to +1. For cosecant and tangent, if you look at the unit circle, blue cannot be 0. Where do you find the blue, right? Where do you see the blue? Right? Where do we see the blue? When will blue be 0? So you look for the blue. When will blue be 0? Oh, here. And there's another one. So we have 2 blues, which corresponds to 2 terminals. And these are the angles that, we cannot terminate there. So that's multiples of pi. Okay? For tangent and secant, the red cannot be 0. When will red be 0? So these 2 terminals, which, the y-axis in both directions cannot be the terminal of the angle. So that's odd number multiples of pi over 2. So there we go. So we have decided from the unit circle how to determine the domain. So that will help us to determine the domain. And of course, we also use ARD, right? We also use ARD. So you can see ARD is very, very important. So now with this review behind us, let's look at the domain of these functions. Oh, by the way, where did I get these functions? These functions are actually from calculus class, okay, Okay, so we're going to see functions with more complexity. Okay, so we're not just having sine, cosine. We're going to have an operation on these functions. For example, in this case, the numerator is cosine, the denominator is sine. Okay, with that, we know cosine is in the numerator, the domain is all real numbers, that's not a problem, but the denominator cannot be 0. So what we can do is that we can set the denominator equals to 0, and whatever solution we get here, those numbers will be excluded from the domain. Okay, to solve this equation, we get sine x equals to 1. Then the question would be, what are the angles make a sine equals to 1, right? So what are the, so you can, if you're good with the unit circle, right? So you can use the unit circle. So where you get the blue number? The blue number is red, it's 1. So this is the terminal that we cannot, the solution would be. So this is the only terminal. So what does this terminal correspond to? What are the angles? So x cannot be, right? So we get x equals to pi over 2, okay, plus 2k pi. So any multiples, right? So we terminate here, we go around, we come back again. So the angles it cannot be for k equals to 0, that's pi over 2. K equals to 1, that's 5 pi over 2. And every time you just plus 2 pi. Those are the angles we cannot, those cannot be, cannot be the terminal. Okay, so that those are, it cannot be those angles. Okay, so now k is integer. Hold on, let me make sure I say the right thing. Integer, right? Now domain. Domain should not include those numbers that make the denominator equal to 0. So that equal we had here now is going to turn into not equal. Okay, so that's it. We're done. Second question, we have 1 minus the tangent. 1 minus tangent. Once again, the setup will be the same. Numerator is 1, so it's not going to be a problem. So we set this equals to 0, right? So anything that costs it equal to 0 cannot be in the domain. So then we have tangent x equals to 1. So then the question is, what are the angles that will cause tangent equals to 1, right? So we're going to determine the terminal. So what are those terminals, right? So we know that's going to be pi over 4 and, 5 pi over 4, right? So x would be pi over 4 plus k pi. That's k pi. Okay, so this is associated with solving, trig equation. Excuse me, trig equations, and k will be integer. Okay, right? So that will be the domain. I'm sorry, that will be. Now we can express the domain. The domain would be that x cannot be these numbers. Okay, so from equal, we change it to its opposite. And go domain determined. Okay. Number 3. What do we do? Number 3, we have cosine x on the top. We have 2 plus sine x in the denominator. So we want to make sure that anything make this denominator equal to 0 should not be in the domain. However, in this case, we need to recall a fact that sine, no matter what's the input, whatever is the x, okay, is going to be between -1 to +1. So sine will never, be -2, in other words, right? So because the range of sine is such, so this equal to 0 is not possible. Okay, so denominator will never be 0. Therefore, the domain would be all real numbers in this case. Okay, so from -infinity to +infinity. Okay, and number 4, domain is that denominator cannot be 0. So we're going to set it equal to 0 and then find the solution and then exclude the solution. Okay, then we're getting cosine x equals to -1. So what are the angles that cause cosine equals to -1? And those will be x equals to pi plus 2k pi, right? Because that's cosine x equals -1. If you're looking at the unit circle, right, it's a pi, right? All right, so we have 6 more. On this one, it's a product of two functions. X squared, of course, is a quadratic function, sine 1 over x. So in this case, it's obvious the domain would be x cannot be 0. That's it. Okay. And number six, x raised to the power 4 is a polynomial. So this domain is also x cannot be 0. Okay. It's pretty straightforward, right? Okay. Number 7, however, we need to consider two things. We have a square root here. Square root is calling for x must be greater than or equal to 0. And this pi over x, that requires x cannot be 0. And these combined, all right, we need to combine these two. So the conclusion would be x has to be positive. And therefore, we got our domain. Okay. Now, number 8. Number eight is an interesting one because this is a composition of two functions. It's a composite of ln function and sine function. So sine function must be positive. Okay, so to determine the domain, sorry, I'm going to remove that. Sine function must be positive. Okay, this involves solving an inequality, but if you look at the figure, if you look at the sine figure, right, sine picture, right? If you look at the picture of the sine function, and you can tell it's periodic, right? We can make it longer. When is it going to be positive, right? So we're going to identify, let me make a bit longer. Okay, so this -12 to +12. All right. So where will x sine x be positive, right? Only those functions will cause sine x to be positive. So what are those? So those are the x must be where? So let me show you. The x must be, make it thicker and make it red, right? So these red will be solution, not including the endpoint. Oh, sorry, my bad. Positive. Okay. So the positive would be here. This piece is a positive, right? So this piece is a positive. So these are the values, not including the crossing, Positive, right? So positive. And the endpoint will be circles. So what are these what are these intervals then? What are those intervals, right? So let's identify these intervals. The first interval, okay, let's start from the one that's easy to identify from. This is from 0 to pi. Okay, so that's from 0 less than x less than pi, right? So this interval. And this is one period, and the next interval would be over here. That's going to be 2 pi to 3 pi. And keep going, okay? How about this interval? So this interval, right? It looks like it's going to be -2 pi. -2 pi to -pi. Okay? And this other one, so this is -2 pi, so this will be -4 pi. So this will be -4 pi. So on this interval is going to be -4 pi to -3 pi. Do we see a pattern? we see a pattern. So we're gonna have all these small intervals, and we have as many as possible. We have infinite numbers of intervals. And do we have a pattern? Okay, do we have a pattern? Okay, so 2 pi, 3 pi, right? And these are the intervals. So how do we express a solution? We could think of a general form to express the solution. Okay, let's see if that works, right? So let's see, this is going to be k pi k plus 1 pi. Will that work? Okay, to see if that works. Okay, so let's test drive it. If k equals to -4, k plus 1 will be -3 pi. That works. If k is -2, k plus 1 will be -pi. That works. If k equals to 0 to pi, and this one will be k equals to 2 pi, 3 pi. So it looks like the solution works. Oops, sorry. Okay, so this would be the general form of a solution where k is integer. Okay, so solution will be x should be in any one of these terminals, then sign will be positive. Okay, so here we go. Let's see, are we almost there? Okay, yes, let's go. 2 more. Okay, these 2 more functions that we get to work with secant and cosecant. 1 over x requires x cannot be 0. Okay, secant. Okay, secant by definition. Okay, secant by definition is r over x. R over x, right? So the red cannot be 0. Or we can also see this as another form. You can see this as x times cosine x. Okay? So with this relationship, if cosine x cannot be 0, okay, cosine x cannot be 0 either. Okay? So what are the numbers will cause cosine x equals 0? Well, you look at the red. One is red equal to 0 when the terminal is on y-axis, right? So on this direction, and x not equal to 1 is set. Okay. And to satisfy cosine not equal to 0, then x cannot be odd number multiples of 2k plus 1 times pi over 2. Pi over 2. Now the question is, will these, how can, if we can combine these two conditions, right? If we can combine these two conditions, to me, it looks like when k equals to, no matter what k is, the terminal, you know, whatever k is, these must be excluded. X not equals to 1 must be excluded. So this is the domain. This is a domain. This is a domain. All right. And the last one we have C because we can see this as x over sine x. Sine x cannot be 0. So one is sine x equals to 0. When sine x equals 0, x is k pi. Right? X is k pi. Right? So you can We can see this from if you are familiar with unit circle. One is blue equals to 0. So this blue equals to 0 and this blue equals to 0. So the terminal cannot be on x-axis. So this is multiples of pi. And that's it. Okay, so k is integer. Integer. Okay. So that concludes some of these functions, or this is the many functions we see in calculus, right, involve trig functions and how to determine their domain. And that's all for this lesson. Thank you for watching.